This video is an introduction to regression. You're just going to get some of the key ideas down, and follow-on videos will get more of the details, and I'll also do a video how to do regression in R. So again, this is just key ideas. The first key idea is that we have a random variable y. I'm going to use a capital letter y. In this case, what's different from hypothesis testing is we didn't have any other variables. Now we'll have some other variables which are not random. I'll call them x1, x2, and I'll use the dots to indicate that there could be more than just two. And it's a probabilistic model. Y is random. So I'm going to put an error term on the end. So again, y is a random variable. The x's are not, but y depends on them. And then we have an error term. For linear regression, the specific form of the function is going to be a linear function. So we have these parameters called beta. So beta naught, beta 1 times x1 plus beta 2 times x2. This is just an example. Beta 3 times maybe x2 squared. And this could go on and on. And again, I have my error term. The reason this is linear, it's called a linear model, because it's not linear in the x's. Notice that we have a square term for x2, but it's linear in the betas. Linear in the parameters. Which we're calling the betas. All right, a couple other notation. The expected value of our error term is 0. So on average, we have 0 error. And the variance of the error term is constant. It doesn't depend on x. And I'm going to denote it by sigma squared. Notice then, if I take the expected value of y, that's just going to be equal to the function. In this case, my expression. But we're not going to have any error term on there. It's just the functional form. Back up at top is the thing I'm calling f of x1, x2. And that's it. What we're going to be modeling is that expected value. Sometimes you'll see it written as the expected value of y given the x's. So it's a conditional expectation. All right, that's the key idea. An example of this might be something x. Let's say x is height. And y is weight. And this is of a male human being. We know as males get taller, they tend to weigh more. So there's a relationship between it. So y would not be a constant mean. The average weight of a male depends on their height. And I'm just going to make up some data. Perhaps the data looks like this. That's just hypothetical. Again, in this case, we're going to say that y is going to be equal to a simple function like this. Our job is to estimate the coefficients. Again, it doesn't have to be a linear function. In this case, it is a linear function in the x. I could have an x squared or an x cubed. It's linear in the coefficients beta, and that's linear regression. Some notation that'll help us. We're going to use lowercase y's, these for observations. So lowercase y sub I is an observed value, and little lowercase y sub hat is a predicted value. In other words, lowercase y sub I hat is going to come from our equation where we've estimated the betas. The betas are population parameters. So it's going to come from the estimated parameters. Our job is to find estimates for beta 0 and beta 1. So back up here in our equation, if we had a line going through here, for this particular point, let's say that's the 1, 2, 3, 4, 5th point, this would be y sub 5. And here, this on the line would be y sub 5 hat. predicted value for that particular x value. If we were to draw a line down, dot dot, for this x value, y sub 5 is the observed, y sub 5 hat is the predicted. What we want to minimize the errors. That is, we want to minimize y sub I minus y sub I hat. This is an estimate of the error, sometimes called a residual. Anytime we minimize, we have to figure out what criteria we're going to use. Some options. We could add up all the errors, so I equals 1 to n. Now, sometimes this value could be negative, sometimes positive. We don't want to add negative and positive numbers. So one criteria would be to take the absolute value and minimize this. If that's difficult, that's an absolute value. Second criteria, which is the one we're going to use, we could take the difference, the errors, and square them. That's a nice mathematical function. That's a quadratic function. So when we take a derivative, it's going to be easier to minimize. In particular, if I rewrite this, I'm going to take my observed minus my predicted, which is my beta naught hat, beta 1 hat x, and I want to find beta 0 and beta 1 that minimize this summation. That's called least squared. This term here is called the sum of squared errors. Sum squared errors. Which makes sense. In the parentheses we have the error, we're squaring it, and we're summing it up. And we're going to minimize that. You take the derivative, set equal to 0. You have to take two derivatives, one with respect to beta naught, one with respect to beta 1. You get two equations, two unknowns, and you set it equal and solve them. And that's how you're going to get the estimates. And software will do that for us. Your textbook refers to the formulas that you need to calculate them. Referring to our textbook, we see that if you took the derivative set equal to 0, beta 1 could be estimated by this expression, where s sub xy is really the sum over all our observations, equals 1 to n. X sub I minus x bar times y sub I minus y bar. And s sub xx, same idea, except I have two x's here, so it's going to be x sub I minus x sub bar squared. And finally, I can estimate beta sub naught as just my average of the y values minus my estimate for beta 1 times the average of the x values. Interpretation, beta naught is the intercept, beta 1 is the slope of my line. And that's an introduction to linear regression.